do you want to describe what you do in a different way?
No, I guess it's in one way it does. I mean, I think it's a facet of what I do. What I really got interested in very early on was experimental physics, because physics does give you a view of the world which is testable, and it's, some scientists would say it's one of the most powerful views that you can have. It's practical, but students sometimes don't get a sense of what physicists do. Reading about it is all very well, doing it is much more powerful. So one of the ideas behind the book was to give students some of the background to experimental methods, some of the skills they need, and have it as a companion, if you like, in the laboratory. Textbooks tend to deal with, that you buy in physics tend to deal with the theoretical side. I think we do too much of that. And my professional life in physics has been experimental, and that's where I've got the most reward, and I'd like my students to get the most reward in that area as well.
So you use the word companion, so the book is a bit like a cooking book companion, like Stephanie Alexander's book, where you really feel like she's in the kitchen with you, giving you advice on the origin of this or that material and how they combine.
Yeah, a little bit like that. I mean, for example, right at the beginning of the book, I give an excerpt of my own. We use logbooks. I use a logbook to record things. So I had a scanned in section of my logbook. Well, no one ever does that. No scientist who writes books in physics ever shows the students what they do. Not undergraduates, maybe postgraduates. You say, well, if you're advocating students use a certain approach, you can only do that with credibility if you're using it yourself. Otherwise, tell them to do something else. Tell them to do what you're doing. So I put that in early on, and in the book, and it sort of it explains, it sort of annotates, gives an idea of why you would do this. So it is a companion. It talks about certain techniques you would use. Way back, it was using one of the first uses of Excel. Everybody uses Excel in science, whether they like it or not, but they use it. Well, I have a very early version of Excel in my textbook because I knew the students would be using it, and we should be telling them about these tools. Tools are important as well. Principles are important, tools are important. And the confidence to be able to use the tools is very important.
So I understand Excel is used for entering data and analysing data.
So you do that, and you can get them to plot graphs. I mean, in science, communication is very important. And communication takes all sorts of forms. It's you and I talking about some aspect of physics which we want to debate, or it would be about, here's some results I got, and trying to tell a wider audience the significance of the results. But you've got to find a clear way to describe and display the results. So Excel does that, but also allows you to analyse the data as well. So it's a bit of a one-stop shop. It's an introductory package, but it's a package everybody has if they've got a PC. Very few people, unless they deliberately take Excel off the machine, usually there's a version of Excel on their PC or their Mac.
When I first asked you to talk to me, we talked about the creativity in science, and my first thought was the experimental nature of science. You come up with some idea and then you test it with experiments. And from my observations here, it's the designing of those experiments. Well, at least that's one aspect of the creative
it is.
nature of it.
I mean, sometimes I think you get a light bulb moment. I think there's all sorts of ways to make progress in science. You can often some of the progress is happened by looking at something that's happened in another area of science and realising that it actually impacts on what you do, and you can steal their ideas and adapt them. So sometimes what looks like an invention or creativity is really theft by another name. But that's important, I think. We should be stealing ideas from each other. I don't mean stealing the work that's been done and appropriate and badging it as your own, but some principles or some techniques that you suddenly realise are valuable to you. So it's the creative use of things that are already there as important as inventing something right from scratch. I mean, if you go back to obviously one of the most famous physicists, Einstein, I mean, he never did an experiment, but he thought things out. It was almost like he was doing an experiment and thinking about the consequences, and then he left it to someone else to actually work out, was that real? Is that something which we can defend or support with experimental work? And a lot of invention is required to test his theory. So invention and creativity comes from the thinking, you could just, say, have a light bulb moment. All of a sudden you have had a thought that no one else has ever had. Well, that happens probably 1 in a million scientists. But you sort of see the world a different way if you try and look at it through another scientist's eyes. And sometimes you can see things in your own area that will benefit from taking work from somewhere else. So the creativity is an imagination. Sometimes is really to do with how you expand what you do and look at what other people have done and adapt it and think where would that fit into my work?
And how would it expand my thinking?
Well,
Does that
yeah.
make
How would it expand my thinking? Yeah, I mean we scientists. I shouldn't really generalise. We like to have cause and effect really well related. We like to know our patch. We like to say, I know this is my understanding of things. And they tend not to want to go outside because they would, for a period, they would be outside the comfort zone. And you don't want to be asked a question you can't answer, so you stay inside your comfort zone. We all tell the students, work outside your comfort zone, and we as scientists don't do that very, very effectively. When we do it, that's when we tend to make some progress, and we get beyond what we know to what we don't know. And so some of the best scientists, I think, have been bold enough to move outside of the comfort zone. And that's where, at those edges, very interesting things can happen. In fact, that's really where a lot of science nowadays progresses. You can't stay as a physicist, you can't stay as a chemist, because you're missing the rest of the things that are happening around the world. I mean, take climate change. Everybody in science can contribute to understanding it and impacting on it. And it's not just going to be the domain of one group that is going to make a difference.
No. And that's actually the focus of our exhibition downstairs. And we're trying to make apparent that it's not just scientists, it's people in the humanities. We're all working away at, we're all responding to the challenge in different ways, either by coming up with new ways of describing it or expressing our understandings, or actually designing solutions like the algal biofuel laboratory.
Yeah, I mean, I myself, I haven't worked in that area, but I developed an experiment for my students, which I developed with CSIRO, which is based on a new generation of solar cells. Not the solar cells you can buy in the shop, but they're looking at new generation solar cells which you could paint on the side of your house or on the side of a building or on your clothes even. That would allow you to convert light energy into electrical energy. So I developed that with the CSIRO because I wanted my students to see the sorts of cutting edge things that are happening in Australia. I actually have hands-on with something of a research nature that they wouldn't normally get a hold of until maybe they're in the third year or honours or doing their PhD. You want people to be scientists. You've got to give them the chance to do science. And I don't mean science out of the textbook. I mean science which is challenging people now everywhere in Australia and around the world. So how do you give them that experience? Well, it's tricky, but it can be done. I like to think that's thinking outside the box. Not what's in a textbook, not what's already in your lab manuals, but things that you say, well, yeah, we could introduce that and expose the students to some ideas which they otherwise wouldn't be exposed to early on.
Do you think with such a force as, or such a concern as climate change, it's propelling us to think more in that way of encouraging our students to be part of this process of understanding and responding appropriately and quickly, rather than waiting for the paper store, the theses to be gathering dust and do it now. Yeah,
I think we're all part of the problem as well as possible part of the solution. How many people drive cars? How many people have air conditioning systems? So we in Australia we do chew up a lot of energy for the size of the country that we are.